Okay, welcome back to this parallel session one on Lisa instrumentation. I'm Rita Dolesi, and this second part we will listen to talks of David Robertson, Henry Schapspe, and Niels Fredrik Hasselmann. The questions will be answered at the end of the presentation. You could write them in the chat, or you can ask the question verbally, just raising your hand, and also questions from the live stream on YouTube are welcome. So I think we can start with David Robertson, University of Glasgow, speaking about optical couplers for LISA.
Thank you, Rita. Let me just find my pointer there. So, as Rita says, what I'm going to talk about here is optical couplers for LISA. This clearly is the work of more than just myself. It's really for the UK OB LISA team. And in particular, I'll point you at Bill Brzezowski, who's done a lot of the modelling work here. So to start us off, the question is, what do I mean by optical couplers? Whereabouts in the whole LISA optical system do they sit? So if you go for this cartoon LISA optical system that I have in the top right-hand corner, you can see there's the laser, the amplifier, the modulation system, whole complicated array of optics there, which I'm just putting into a black box. And they produce about 2.5 watts of light that comes out through a single mode optical fiber, this Newfern 1060L fiber, and the beam inside that diameter is constrained in a core of about 8 microns diameter. And that brings the light down onto the optical bench. And on the optical bench, what happens is you have to take this light from the optical fiber and produce a free space beam that is a diameter of about 2 millimeters. So you have to expand the beam up a factor of about 250, and you have to collimate it extremely well. And that beam largely then goes on, it does various other things in the optical bench, which we will ignore entirely. And the main power actually goes straight to the telescope, where again the beam is expanded up and transmitted to the far spacecraft. Now, as we've seen from Jeff's talk earlier, the constraints on the beam that's transmitted to the far spacecraft are extremely tight in terms of wavefront quality and so on. And that in turn means that there are tight constraints both on the telescope and on the beam on the optical bench and how well it matches to the telescope. And that's largely what I'll be talking about here. And just as a reminder from Ewan's talk earlier, the optical bench is a little more complicated than I've described it. The other important thing for the optical couplers is that a little bit of the beam on the main optical bench goes to a second optical coupler that transmits light through a fiber to the adjacent optical bench on the same spacecraft. And this allows us to do the phase comparison essentially between the two lasers on the two different optical benches. So that gives you a rough idea. In practice, what's an optical coupler look like? Well, again, there's this very simple sketch diagram here in the top right-hand corner. Essentially, all that you need is an optical fiber with a very nice end on it and the appropriate lens at the appropriate distance from the fiber with the appropriate orientations. And that will produce a beam that has the right physical properties. And here, particularly, we're thinking about the waist position of the beam that comes out of this assembly and the size of that beam waist. And I've listed in the left here some of the requirements that there are on the resulting beam. And in particular, for matching to the telescope, we need to know where the location and the size of this beam is with, well, it doesn't look like huge accuracy in terms of we want to be able to place the waist position within about 0.3 of a meter. But it turns out for a beam that's the size that we're dealing with, about 2 millimeters diameter, that's actually an extremely tight requirement. It requires that the fiber to lens spacing is constrained to within less than 10 microns typically. And there's a whole pile of other constraints that also come along with it in terms of the the beam quality, this wavefront flatness, the beam pointing stability. Obviously, it has to be able to handle this 2.5 watts of optical power. We want to minimize the number of surfaces in the optical path in total. Every time you have an optical surface, you have the chance for scattering, you have the chance for a little bit of loss or whatever. So we want to minimize the number of optical surfaces that the beam goes through. And we also want to, as far as possible, minimize the power density on those surfaces as well. You're much more likely to have laser-induced power damage if you have very high light intensities on particular surfaces. And another thing we want is to have extremely low scatter and backscatter from it. That's another important constraint. So, as you'll see in a couple of the slides already, the system we've gone for is, as you can see in the picture here, essentially almost as a bonded together. It's using hydroxy bonding to bond together a block in which the fiber is mounted, some few silica, essentially lumps, very carefully known lumps that produce, essentially control the optical path and the lens on the end of it. And the reasons we've gone for this particular sort of construction, there's a number of different reasons that are driving it. As I said before, we need to control the spacing essentially between the end of the fiber at this interface here and the front face of the lens. We want to control that to of order 10 microns or so. We need to be able to adjust that. In the end, we will need a custom lens. At the moment, we're using off-the-shelf lenses, but for the particular requirements for LISA, we'll actually need a custom lens, and I'll come back to that later. Pointing stability, again, I said was an issue. If the beam from the fiber coupler is changing in orientation, then obviously that changes the alignments later on down the optical bench, and that can lead to problems. So there's quite a tight requirement in that, and we meet that quite nicely. So for various reasons, we've gone for this quasi-monolithic construction where we have hydroxycatalysis bonded the fiber, the spacer, and the lens all into one unit. And that has a number of advantages. It keeps the lens and the fiber end very tightly constrained relative to each other, so you don't really get any beam pointing changes with, for example, temperature changes. It minimizes essentially the interfaces we have between glass and air. Essentially the only interface you have in this is the final output of the lens. And it also means that the beam power density at that is very low. In LISA Pathfinder, for example, essentially we had a naked fiber end, a space, and then a lens. And there, the power density at the end of the fiber was about 300 times what we'll get, even with the much higher laser power we're using in LISA. And also the backscatter from this assembly, and there are measurements which I'll point you to later, is extremely good. So to give you an idea of the build process, as I said before, we have the optical fiber you can probably see here coming up, mounted in a fused silica block. And then once it's been mounted in there with very tight constraints, the front of the block is polished very, very flat, and we bond a cover slip onto it. And that means already that the fiber end is protected from damage or contamination or whatever. Then in order to control essentially the waste position, we need to control the spacing between the fiber end and the lens. And that's kind of what you're seeing in this picture in the second, in the top right-hand corner, where we have the fiber essentially beam expanding out of that, and we have the lens held in front of it. And there's kind of two things we're doing here. The lens is mounted in a hex pod, so we can control its orientation, its lateral position, its angular position, and maneuver it around so that we end up with a beam out the front of it that's something close to what we want. It doesn't have to be exactly right, but something close. And when we have that, we do two things. We measure the separation between the lens and this fused silica block with some micron level precision. And we also characterize the beam out here. We take about 8 or 10 measurements at different distances along the beam. And we're doing this with specific pairs of lenses and sort of fiber assemblies here. We then take all this data and throw it at a model, which I'll come back to in a moment, and we use that to predict what length of spacer we actually want to get the required waist that we're looking for. So that's why, even though you're measuring putting this thing up, measuring the beam out here, it doesn't have to be exactly right. As long as your model can predict what you need to put in as the space from these measurements, then that's enough. So as I say, the next stage is to try and make sure that the optical path length in glass is exactly right at the few micron level. And we do that using this slightly wedge-shaped block here. So the wedge-shaped block is pretty much exactly the right length, but to do the final adjustments, we can either essentially slide it up or down the slope a bit, and that changes the optical path length through the block. And that's how we control to the precision we need at a couple of microns what the optical path length is in the glass. Then finally we bond the lens onto the front of it. So a little bit about the modeling. I'll not do a huge amount about it, but there's been a lot of work gone into this to make sure that the model really reflects reality very well. So the modeling is done in Zemax using its physical optics propagation module. And it's actually an iterative process where there's a MATLAB wrapper around the whole thing that optimizes 6 parameters to optimize the fit. So we've got quite a complicated fitting process, and you can see some of the output from it here. Essentially on the top right hand corner, it's the errors in the fitted parameters and how they're reducing in size as the number of iterations goes up to about 40 or so. The fundamental output from all of this is, does the model actually fit with what we're getting? So on the bottom right hand corner here, you can see one of our very good results, in fact, where the blue line and the blue crosses are the actual achieved results for the beam profile, and the red ones are the target measurements for the same thing. So you can see it is actually an extremely good fit, and the waist position actually is, in this case, to within about 40 millimeters of what's required, which is well within our requirements. So the model is very good for building up and producing what we want in this particular case. We also want to use the model to design a custom lens so that we can actually get the final beam size that we really need for LISA. So I will skip pretty much over the pointing stability one. This is old results. We've reported these before, just to say that the pointing stability is a factor of 3 better than required for an optical coupler of this type. That's measurements we did some while ago. This one, it amuses me slightly, to be honest, that the waist position and size surprisingly sensitive, and in particular here we're building the thing up, we're doing all the measurements with the thing in air because I work best in air, but it will in the end be used in vacuum, and air and vacuum have very slightly different refractive indices, and you put it into the model and you discover that refractive index is very slightly different, and you would predict that that would shift the waist position by about 100 millimeters. And as part of our model validation, we set out to try and test this. So we took one of our engineering models of the optical coupler, we put it into a vacuum system and essentially measured the waist position with air in the vacuum system, then evacuated it and expected to see a shift of about 108 millimeters. We saw 110 millimeters, which is astonishingly similar. Admittedly, the errors are quite large, but it's still showing the modeling is predicting the right sorts of things, which is very nice. We also worried about the temperature of it, and we changed the temperature by about 20 degrees or so, 25 degrees actually, and that produced almost nothing, as you would have predicted. Another step of model verification that we tried was to take two different optical couplers and essentially point them at each other. And if we put the second optical coupler onto a hexapod so we can align it in angle and displacement, then we can optimize the coupling. But what we can then do is, once we've optimized it, we can actually change the alignment by either displacing it in angularly or laterally and see if the change in coupling corresponds with what we would expect to happen from our model for these particular optical couplers. We've actually done this with essentially 3 different pairs. We've got optical couplers that are significantly different in terms of waist size because they're using different components, so that's what we would expect to have. But we can use that as an extra way to exercise the model by doing coupling between like couplers and between unlike ones. And in particular, a really nice result on the right here. The blue data is the prediction from the model. And you can see we're getting a coupling efficiency from one to the other of just over 90%, which is extremely good. But also the thing that I really like about this is that the red line you can see in this graph, or can barely see, is the lab data. And even for very large misalignments where the coupling has gone down from 90% to about 30%, the model and the lab data are agreeing extremely well. Put this in just to give you an idea of what I'm not telling you. There's lots of details in this that I don't really have time to go into, which I've only got a couple of minutes left, I think. So there's detailed measurements of the pieces and exactly how we do that. There's a lot of detail in the modeling about the fact that the beam is not Gaussian. Some of the parameters are quite strongly coupled to each other and so on. Another detail is it's surprisingly hard to measure beam diameters. Different cameras will give you different results, particularly using different technologies. Different algorithms, even in the same data, will give you different results, and we spent quite a lot of time working through that. Not going to say anything much about backscatter and radiation testing, except to say that these have been done. They've worked out very well, and I would strongly encourage you to go and look at Max's talk, where he goes into much more detail in exactly how he's done these and how well everything has worked. So I'll finish here with just summarizing the whole thing. So I would say that building and modeling optical couplers to LISA specification is a very well controlled and very well modeled process. And having this modeling that's working really well is absolutely critical, because we need that model to specify a custom lens that we'll actually use for the LISA files. And that's something that we have now specified and is now under manufacture. I suppose the part of that, reality and modeling agree. That was absolutely key to the whole thing, that you actually get the modeling that works very well. As I say, it's been used to specify the components for actually a final LISA specification optical coupler. And with that, I will finish and ask for any questions.
Thank you, David, very much. I'm really impressed by the progress made on the implementation of the optical bench, hearing from you and also from the talk of Yuan today. We have a question. We have 2 actually. Alexander Schultz, is there a reason to prefer refractive over reflective fiber couplers?
Yes, I think it might seem a slightly odd reason. I think one of the reasons that I alluded to earlier is that we don't want at some point you have to get light coming out of the fiber. And it's quite dangerous, I think, to have very high power densities. You're very much susceptible to laser-induced damage or contamination in various ways. So by having all of the expansion of the beam up to the millimeter scale or 2 millimeter scale happening inside fused silica is much, much safer in that sense. And it's essentially, once you've got to a lens surface at the with a beam of the 2mm scale, you can, it's a much easier surface to manage, to clean or whatever.
Thanks, David. Then there is another one. We have a time just for a quick answer. Paul Fulda. Well, then you have others, but maybe you can take them offline. Paul Fulda is asking, is there anywhere one can find your results on the differences between beam diameter measurement methods?
No, I think is the short answer to that. It's something we spent quite a lot of time doing.
Contact directly David to have.
Absolutely, yes. No, I'm more than happy to talk about it, but it's not something that's written up directly, I'm afraid.
Okay, maybe just a quick answer also to Jennifer Lee. How is the optical coupler held on the bench? Will there be packaging around the assembly you show?
Okay, so I think both you and I sort of mentioned in passing hydroxycatalysis bonding, and that's how the optics will be secured to the optical bench. And that's actually, if you look carefully at the design, you'll see that there are polished surfaces perpendicular to the beam direction that will be used to hydroxycatalysis bond the fiber coupler strictly onto a post that goes onto the bench, but we bonded onto the bench in that sense.
Okay, clear enough. So thank you, David, again. And we move to Henry in Chauspé. I hope I pronounce it correctly.
That's perfect.
Okay, and he would talk about measuring differential acceleration on board LISA spacecraft, application to defects optimization and acceleration noise estimate. Henry is now at the Heidelberg University.
Yes, thank you, Rita. Can you see my screen well?
Perfectly.
Okay, perfect. Thank you. So yes, today I'm going to present a work that I've been done in collaboration with Martin Newitz and Orion Sauté and Peter Vass from AEI and University of Florida. This has been subject of research that just was out today, so that's perfect timing. And so the topic is like developing ways to measure differential acceleration aboard the LISA spacecraft with two applications in mind. One, for optimizing the suspension part of the control system. And one is deriving a way to build estimator of the acceleration of the test mass on board. So just a very brief recap of what is the LISA detection principle. So the basic idea is to realize in space a basic sketch of interaction between matter, meaning like you have a ring of particles, and this ring of free particles that deformed by a gravitational wave passing through. As particles, we have the spacecraft, of course, and not a very good reference of inertia. So we house on board reference of inertia, which are the test masses, which have very good level of stability. So that part have been tested with LISA Pathfinder, verifying that, so shrinking one interferometer arm of LISA into one bigger spacecraft, we were able to see that the differential acceleration between the two test masses was compatible with the astronomy. But of course, with LISA, because now the test mass to test mass is 2.5 million kilometers apart, and it's broken down into three pieces, so test mass to spacecraft, spacecraft to spacecraft, spacecraft to test mass. We have much room for optical misalignment and geometrical imperfections that leads to imperfection and coupling to stability of the spacecraft, which was not the case for LISA Pathfinder, in particular T2. So here for LISA, spacecraft stability is a key properties, and understanding well the cloud dynamics of key importance. So in that particular context, this work have been focusing on optimizing the defects and defining properly first, as the first step, control coordinates, in particular to mitigate suspension, to isolate suspension from spacecraft jitter. That would be the point today. So here you see a sketch of the spacecraft, a slice of the spacecraft on the XOY plane, meaning it's a plane which is parallel to the solar panel or within the constellation and triangle plane. And so you see three bodies. There is in the identical system, you have the two test masses that are housed in like square cubic electro housings that are attached to the telescopes. And so the point of the control laws is to make sure that the test mass are at the center of the housings. They're well aligned with the inner wall of the two housings. The telescopes points towards a distant spacecraft. And that's pretty much it. So you have all these constraints. So to measure the test mass position, you have two types of sensor. You have optical sensor on the axis of the telescope. We provide a picometer for correlative precision, so that's the best sensor on board. You have also capacitive sensing, electrostatic sensing. So we provide more like nanometer and nanoradian precisions, both for longitudinal and angular displacements. And you have DWS, so long-range differential waveform sensing, that basically measures the incidence angle between the incoming beam from distant spacecraft and the photodiodes on board. And these two angles provide you information about the attitude of the spacecraft. So that's the basic idea here. And from that information, well, first on this sketch, I want to stress that two very important reference frames are the one attached to the spacecraft, which is the spacecraft frame where the x-axis points towards the bisector of the two telescopes. Z is normal to the solar panel and the Y is completely infrared. And you have also frame attached to the housing. That's where the test mass coordinates are defined. So X points towards the telescope axis and Y and Z are completely infrared. You can see that on the figure. So this sensor information are used to control the test mass. So whenever you see differential motion between the two test masses, you have no choice but to apply force on the test mass to correct this differential displacement, and that is done with electrostatically acting on the test masses. That's called suspension control. And whenever you see a common mode motion of the two test masses, it basically means that the spacecraft is moving, is shaking, and that you can control in correcting the spacecraft motion with micropropulsion, and that is called drag-free. Okay, that was so yes. So basically, that's what is DFACS, drag-free and attitude control system. Three main points: mitigate spacecraft jitter, that's drag-free. Maintain the spacecraft telescopes well oriented towards the spacecraft, that's attitude control. And compensate test mass drift one with respect to the other, and make sure they stay in place in the spacecraft, and that's suspension control. So we wanted with this work to optimize the DFACS coordinates in order to make sure that this common mode control, drag-free and differential mode suspension control are well isolated, so that you don't trigger force on the test mass, which come from which are triggered by the spacecraft agitation. So that you don't want to do, and in doing so, you mitigate the amount of force which is applied to the test mass. So you're defining very well common mode and differential mode. And to do that, the point is to build estimator of what is the differential acceleration you measure on board between test mass and test mass 2, test mass 1 and test mass 2. So that's a way of optimizing suspension. Instead of like purely suspending test mass on the motion you see of test mass 1 along the three axes Y, X, Y, and Z, you take all your sensors on board and you build estimator of what is the differential drift between the two test mass, and that will serve as a locking information for the suspension. So you end up with some coordinates here. So you see, for example, the main coordinates of interest here are the suspension one. So if you look at the bottom left equation here, which is a coordinate for longitudinal suspension, you have also a big picture showing all the coordinates, which is a bit busy, but you can find main coordinates, in particular theta, eta, and phi, which are respectively always rotation around X, Y, and Z, just for your information. So here, basically, the red square here is a measurement of the differential displacement between test mass 1 and 2 projecting along Y. Y will be the axis for suspension control. And you make use basically of the other test mass in order to measure against the observed differential acceleration projecting along Y. And that will serve as a quantity that you want to suspend. But when you do that, you have also another component you're not taking into account, is the fact that when you have your spacecraft rotate, it also induces an observational differential displacement with two test mass from a lever arm, and you need also to correct that in order to build a correct estimator of the differential acceleration. So that's the green component you see on the bottom left, and that you make use of the long-range differential waveform sensing, giving the attitude of the spacecraft. So that's the main part. For the suspension control, this is the same idea, except that now you want to be isolated from spacecraft jitter, but you still want to keep on with the rotation of the constellation around the sun. And to do so, you basically will make the difference between information of the rotation of the spacecraft from long-range TWS with difference from that with the test mass DWS, so the local measurement of test mass rotation. And if you do so, you're able to reject spacecraft jitter and still be sensitive to the rotation of the spacecraft. Okay, so here are the full drag-free control coordinates we came up with. And now I'm going to demonstrate that using these new coordinates, we're able to confirm that we isolate suspension, so application of force on test mass from spacecraft jitter. We still, yes, so the rotation of the constellation will still trigger force on test mass, both in rotation and in longitudinal, in order to keep on, to rotate the constellation around the sun that we want to keep. That's a common mode suspension we want to keep. And that we still have the same term of stability of the degree of freedom. So for that, we use simulation tools that have been developed from for the consortium. One is purely linear, done in MATLAB, which is called LISADIN. It's enough for all the application we want to do in that work. But just for cross-check, we also use a full simulation for LISA SimScape, which is the full geometry of the spacecraft and full nonlinear equation of motion. And both simulators agree on the fact that this new scheme is running well. So this simulator basically simulates the closed-loop dynamics of the system. So this feedback loop you see here, and I've been mentioning. And the idea is like to solve for the time evolution of the 50 degree of freedom, meaning attitude of spacecraft and longitudinal motion of test mass and angular motion of test mass of the two test masses. Okay, so first experiment we did, we injected a sinusoidal force on the spacecraft and verify what would trigger in terms of suspension force on test mass. If the thing is well done, then we trigger no force. So here you see the comparison between blue, red, and yellow. Blue was a simple scheme where you basically suspended all the degree of freedom, so that's a naive one. And the yellow one is like with this new scheme. And you see that the two lines we injected at 10 and 20 milliamperes completely disappeared. And the red one is with and without. So comparison between the red and yellow is with and without the level of correction. So you see that well, here we didn't eject a torque, but you still have a noisy torque coming from the source noise. And you see that it in the case you don't correct for the lever arm, you still trigger some special suspension which are coming from the jitter. And so if you include this lever arm, it is optimal. So you can do the same experiment for the attitude, and it works perfectly well. So that's an analysis we done in a paper. Now you want to verify that you're rotating well your test mass with the constellation around the sun. So what you do to simulate that is you inject a guidance at low frequency, a guidance of the for rotating the spacecraft at low frequency, and we can show here that so indeed this guidance triggers some suspension forces and suspension torque on the test mass that go along with this guidance. So effectively, you're gonna have suspension force and torque that will accompany the rotation of the constellation. So that we keep. And then with the same experiment, we can check for these two same degree of freedom. So here, this is Y motion, test mass along Y, and rotation around phi. That for the simple and optimal scheme, we keep the same level of stability. You see this peak here. This is just the guidance we inject in that experiment. This is not of interest here. So the stability is the same. So if you look at the impact on noise BJ, the main impact is that if you have some actuation crosstalk, now because so all the actuation crosstalk contribution that come from noisy spacecraft motion which suspension C and apply some unnecessary force. All that is completely cancelled with a new scheme. So there was not a limiting contribution to the budget, but now, because it's completely killed, we gain in robustness in more general. That was the idea. Now we can use the same philosophy to build estimator of differential acceleration, which is the test mass, but now projecting along X. And for what purpose? Now it's building an estimator for the acceleration noise now. And so this is the same type of equation you see here. So you use both the test masses to measure one respect to the other, the acceleration, and you correct for the lever arm. That's the same idea. And here we also correct for the commanded force here, because we want an out of loop quantity. So so this is not the acceleration you're measuring. This is a little bit. This is an upper bound to it. Because you also pick the acceleration noise of the second test mass partially along y-axis, along the y-axis. But still here is giving you a good idea or an upper bound of what would be the acceleration noise, and can be very, very interesting for sanity check and also commissioning calibration. And so you can have a certain measure of the force you apply during calibration on your test mass. And that's super interesting. So to verify that this equation here were able to reproduce the force which are applied to the test mass, the noisy force are applied to the test mass, we did an experiment again. So we applied a sinusoidal force. I cannot see the amount because here is my, anyway. We applied the sinusoidal force on the test mass, and we checked if our estimator was able to recover this, and that's what you see here. So we were able to observe this. Of course, there is more noise, as I said, because you're also picking test mass, some of the second test mass noise. But still, this is a very, very interesting estimator. You can build a spectrum of it, and you can see indeed that you're able to pick to correct for the injection you see. And as I said again, compared to the true acceleration noise of one of the test mass here, you're like a certain factor above in terms of noise, because you're picking more noise in this emitter than the true acceleration noise you want to recover. Here in the paper, you have a whole analysis of decomposing all the contribution to the estimator and verifying that everything is. Okay, I think I'm pretty much done here. I will conclude this just with the fact that, so building this estimator of observing directional acceleration was able to define better, more subtlety facts coordinate in order to make a better clear distinction between what is common mode and what is differential mode. And in doing so, we were able to suppress completely actuation crosstalk driven by space half motion. And doing so, it was enhancing robustness of LISA performance. Advantages of this scheme is it's purely software processing. I mean, it comes almost at no cost. And if anything, I mean, in any case, you can change the scheme in flight for whatever reason, if you have failure of sensor or whatever, that's always something you can do. Possible disadvantage is the fact that now, because you for each of the coordinates now involves all the sensors, it make me maybe harder to interpret your closed-loop system at the end. But in any case, you have all the coordinate mapping matrix, which is pretty analytical, so you always can refer to that in order to better understand your closed-loop system. About the estimator of the differential acceleration, like it puts a very interesting upper limit on your performance of the test mass acceleration for both axes here, and it's also a very interesting estimator for calibration and data processing. Like if you want to measure a force you're injecting on one axis, or if you want to detect glitch, for instance, it could be very interesting to have this new observable. If you want to know more about this work, you can check out our new paper just out today. I received the notification this afternoon, so you can just follow this link to have more details. Well, thank you very much.
Thank you, Harry. Thank you very much. Very interesting questions. Alexander Schultz, have you performed a model with shape noise as well? You stated only white noise. I would expect many noise sources contribute 1/f, which would be important to consider.
Yeah, so most of the noise is there some in the paper we specify the shape of all the noise. And as much as possible, we took LISA Pathfinder like noise shape and values measured with LISA Pathfinder.
Okay. So you are measuring you are measuring estimated differential acceleration between the two test masses along a certain degrees of freedom, right? Along a certain direction.
Yeah.
So, but because I was confused by you saying because you were measuring acceleration noise locally, so it's a differential acceleration that you are measuring.
It's differential, but it's still locally. It's differential between the two test mass in the local spacecraft.
Okay, in that sense. Okay.
Yes, so that's why you have to pick a little bit of y acceleration of the second test mass, and that's your estimator is not perfect. That's what you see here, but still that's some info you may want to use because everything is purely local, and you have an idea of what is your acceleration noise. Okay.
So Alexander was also asking, are the models made available in the scope of the publication?
The model, the dynamical model, or the noise model?
I don't know, Alexander, would you? Alexander Schulze, would you? Steamscape.
As a Steamscape, no, I think it's still private. It's a, I mean, it's consortium. It's public for the consortium member. That was developed by Martin Hewitson, so it might be better suited for than me to answer this question. This is specific.
Okay.
The linear one is accessible from people that are LISA membership.
Thank you for the answer, Alexander.
Thank you.
Okay. Thank you, Harry. Very interesting. And now we have the last talk of this session, given by Niels Friedrich Hasselmann of Airbus. And the title of the talk is Active Beam Pointing Control for LISA via Interferometric Angle Measurements. We can see your first slide, but it's not in the presentation. Great. Please. We can't hear you yet. Frederick?
Okay, can you hear me now?
Yeah, perfectly.
Okay, perfect. Thank you again for the kind introduction, and welcome to my talk about active beam pointing for LISA using differential wavefront sensing as feedback. And here in this picture, you can basically, in the photograph, you can see the setup that was used to obtain the data. I will show you later. And a little fun fact, maybe, so the interferometer you see in the front on the right, yeah. Some components should look familiar from an earlier talk given by Ewan. Here's the fiber launchers from Glasgow. And this interferometer was actually bonded by Ewan. Yeah. So, okay. So let's have a look at what I will talk about today. So first, I will give you a brief introduction to the topic. So why is active pointing required, and what solutions do exist to tackle the problem? And what are the challenges that are coming up? Yeah? And then I will present to you the experimental setup in a little bit more detail. So I will talk about the layout of the setup and the function of the components. Then I will talk a bit about tilt-to-length coupling for small field angles. And this is highly interesting because it helps us demonstrating the feasibility of the alignment of a LISA representative telescope using TTL coupling effects. Yeah. And this is then followed by the alignment of the mechanism showing or simulating reenacting the motion of the distant spacecraft. And I will talk a bit about the challenges and techniques that were that occurred or that were used in the alignment integration and testing of the spacecraft simulator mechanism. And then I will show you the first data on active beam pointing that were obtained using the now completed system. And so this data is incredibly interesting and exciting because it helps raising the credibility of the mechanism technologies that are used for active beam pointing. And in my outlook, I will tell you what is next. So let's jump right into it. And so, as you may remember from Linda Mondin's talk yesterday, I think, so the inter-spacecraft angles or the apex angles of the LISA formation vary slowly over the mission duration due to orbital perturbations. And this requires that the telescopes must be continuously aligned to point at the distant spacecraft in order to maintain the noise levels required for LISA. And the solutions that were conceived to tackle this problem were telescope pointing, siderostat pointing, are also in-field pointing. And telescope pointing is a baseline architecture for LISA, where the whole telescope modules are basically pointed or moved. And in siderostat pointing, the first mirror that is encountered by the incoming light from the distant spacecraft is a folding mirror, and this mirror must be rotated and also operated in an additional linear axis, so it must be stepped. There's a stair and step motion going on of the linear axis in order to keep the TTL coupling low. And in in-field pointing, a very small mirror is positioned in an intermediate pupil plane of an off-axis telescope and does the beam pointing, reducing effects, for example, of self-gravity, because we only are moving a small mass. And all of these architectures have their benefits and drawbacks, but I don't want to talk about those today. I want to focus on what these architectures have in common. And all of these payloads require active closed-loop beam pointing using interferometric angle measurements, and they all suffer from TTL coupling. However, the in-field pointing concept enables end-to-end investigation of tilt-length coupling effects in a laboratory environment on ground, and also allows us to have a look at the alignment procedures for a typical telescope and measuring the pupils. And however, this is a cool thing, the results can be transferred to all the architectures. And with that in mind, let's have a look at the in-field pointing setup. So the experimental setup is shown in the top here as a sketch. Can you also see my mouse, by the way?
Yeah, okay, now, okay. Oh, now it's okay. So we are looking at the fourth slide.
And can you see my mouse, my pointer?
Yeah, we can see the mouse, yes.
Okay, perfect. So I will use this as a laser pointer. So here you can see the sketch of very much simplified of the setup. And on the bottom left, you can see a CAD model of the entire setup. And on the right, there's a picture of the fully integrated setup. And the setup consists of the spacecraft simulator reenacting the motion of the distant spacecraft, to be seen on the right here, and an off-axis telescope that is reflective and has a magnification of 5. And in the intermediate pupil plane here, there's the so-called in-field pointing mechanism placed that does the pointing. And then we have a refractive 5 times magnification stage, and another pupil plane in front of the interferometer. And the interferometer here is shown very much simplified. So we have also auxiliary interferometers that are not shown here for the reference interferometer and a phase interferometer. And and so the interferometer has some optics here that are polarizing for beam steering, and another relay stage to complete the pupil imaging onto the quadrant photodetectors. So in total, we have 4 pupil planes the first pupil plane being the one on the QPD level here, then one between interferometer and beam expander, and the third one being where the infield pointing mechanism is placed, and last but not least, the pupil where the spacecraft simulator sits in. Yeah, and so here, for example, the beam expander cannot be seen in the photo here because it's hiding behind the reflective stage, but you can see it here on the left. Yeah, on the left-hand side on the CAD, you can see it. It's sitting behind the reflective telescope. And I want to mention that all these, so we have mostly an all-zero dual transfer function, and when there's metal, it's always like formally compensated. Yes. And now we are using the interferometer readout, to derive, for example, our differential wavefront sensing signal, and that we can use for controlling the mechanical angle of the infield pointing mechanism, thereby performing the pointing. We can also, for example, apply a command to the spacecraft simulator in order to simulate an example as an orbit of the distant spacecraft, so to reenact the motion of the distant spacecraft. Yes. So one measurement that's highly interesting now is the tail-to-length coupling for small field angles, as it allows us to demonstrate or to perform a measurement of the total system pupil offset, as well as to determine the pupil calibration accuracy. And also it allows us to show an effective telescope and optical bench alignment integration and testing, especially with respect to pupil alignment. And yes, and this is something that is really of interest for integration of LISA also later. And the measurement conditions here were that the spacecraft simulator is static, while the infield pointing mechanism is actuated, and this is happening typically at 5 microradians per second mechanical angle. And now we record the change in path length as well as the angle between the RX beam and the local oscillator beam by means of the quantum photo diode signals, so differential wavefront sensing. And we perform a double pass through the setup. And so here you can see now the differential wavefront sensing angle in milliradians plotted versus the optical path length. And the slope of this data set gives us now the linear TTL, which is about, in this case, about 3.3 micrometers on interferometer level, on optical bench level. And if you transfer now to LISA, where we have a magnification of the telescope of 135, for example, you would obtain an external pupil offset of 0.45 millimeters, which is well within the LISA requirement. And the error is well below 100 micrometers. So although the accuracy is well better or well below the requirement. Exactly. So and this shows that for the ORATM, for example, and palm actuator, as well as for the hinge design, the lessons that we learn can be transferred to those, and the designs are very similar. So they are always like these solid state hinges are always used, Haberland hinges in combination with some bimorph piezo drive. To measure now TTL over large field angles, because the field of view of the interferometer is of course limited to 0.5 millirads appropriately plus minus. What is required is to reflect the beam back in itself, and this can be done by tilting the spacecraft simulator accordingly. But in order to do that, to tilt the mirror sitting in the external pupil, we first need a mechanism that does that. And this mechanism has also to be placed in the setup and aligned. And the optical tools we used for alignment were a laser tracker for the X, Y, and Z position, and the interferometer using differential wavefront sensing again to control the tilt in NIC and yaw. So NIC would be, if you look at, for example, the hinges here, these hinges, when so around this axis, if you connect the hinges, if you tilt the mirror around this axis, this would be NIC. Yaw would be perpendicular to that in this plane. And if you rotate the mirror around the surface normal of the mirror, perpendicular to both axes I mentioned before, then this would only contribute to the wavefront error slightly, and yeah, over higher terms. So this doesn't really have to be aligned that well. And for alignment, we used as mechanical ground support equipment, we used micrometer screws, and we also used a small rubber hammer to knock against the zero-dur component, so that it basically slides into place using slick tip, yeah, and that can also be used to align the setup. So you knock it around until it's there with micrometer precision where you want it to be. And so the characterization of the parasitic hinge deformation that always occurs using these hinges can be done before placing the mechanism in the setup. However, if you look at TTL measurements later, you can use certain measurement protocols that ensure that the parasitic motion of the spacecraft simulator mechanism doesn't contribute to the system TTL. And you can furthermore extract also the parasitic effects caused by the infield pointing mechanism, so the mechanism used for beam pointing. If you have questions about this, I'm happy to answer them later. And so let's have a look at the first data recorded for active beam pointing, or the demonstration of active beam pointing. And here the goal was to demonstrate zero DWS control or DWS control. Thus demonstrate basically an end-to-end laser previewing angle compensation. And the measurement conditions now are that the spacecraft simulator is actuated in open loop, and so typically with a speed of some micrometers, nanorad per second. And the infield pointing mechanism is operated in closed loop operation to keep the differential wavefront sensing error angle at zero. And an optical encoder measures also the mechanical angle of the hinge of both mechanisms at all times. So there are two optical encoders, one for each mechanism. And so on the left here, now you see that basically, if you look at the gray curve, that depicts the case where the telescope is static, so meaning both mechanisms are resting, and the red curve, where basically the spacecraft simulator moves at a constant speed, while the infield pointing mechanism compensates. You see that there's not really a difference, a vast difference between the two data sets, because this is an angle that is perpendicular to the basically controlled one. And if you look at the horizontal angle on the right, you can see that now the in-loop angular noise follows now a shape that would be expected by using a PI controller in the frequency domain. So 1 divided by F noise becomes white noise, for example. Yes, and when for low frequencies we are limited by electronic noise. So we are sitting here on the reference and phase interferometer, on the auxiliary interferometers on the noise sphere. This can be seen from the comparison in the frequency domain, and the performance is now expected to be mostly limited by the control scheme as well as electronic noise of the QPD. So the control scheme is here a PI controller, but one could think, of course, of a more advanced control scheme. That's probably not really required if you look at the data, because it's well below the requirement, actually. Yes.
Frederick, I'm sorry to interrupt.
Okay, but we're already at the outlook.
Because we ran out of time, so please, if you can go quickly to the.
I can do it very quickly because we already arrived at the outlook. Yeah. Okay. So what's up next? So next we will measure the system TTL over the entire field of view by tilting both mechanisms macroscopically. So this requires, of course, much faster actuation for reasonable measurement times, but both measurements are expected to be performed by August or September this year. And to further validate active beam pointing, out-of-loop measurements are planned, which couldn't be done so far because, as you see, the last relay stage is only mounted in front of one QPD. The other one, the QPD on the right, there's no relay. The pupil imaging is not completed because we still wanted to do measurements of the longitudinal pupil positions. And but this will also be done, and then we can do balance detection as well as these out-of-loop measurements. And last but not least, we will investigate the impact of nonlinear TTL. That also depends on the method on calculating the differential wavefront sensing signal, actually, and also the alignment strategies may depend on how you evaluate the DWS signal. Yes. Okay, and with that, I would like to thank you, and questions are welcome.
Thank you very much. We use also the time for questions. So David, I see that he raised his hand. Please, David, ask your question. I hope that the answer can be quick. Go ahead, David. You are muted, David.
Was that this, David? You were...
Yes, David Robinson, you raised your hand, but maybe it was not.
No, I didn't raise my hand. I was just applauding. I enjoyed the talk.
Okay,
thank you.
Okay. So we have a question in the chat. Philippe, can you elaborate why no acousto-optic modulator was considered for the beam pointing as the Japanese are planning for the cavity scheme?
So, yeah, that's a good question. And so the acoustic optomodulator, let's think about it. So for pointing, actually, so when we look at the angular stability, it should be possible to arrive at an anurat stability levels, yes. But for the path length stability, because you're dissipating quite a bit of energy in the acousto-optic modulator, and which leads to thermal noise, and that in combination with the relatively poor coefficient of thermal expansion, and that combined with the change of refractive index over temperature, will result in several picometer probably of path length fluctuation, violating the LISA requirements already. So while the pointing stability in terms of nanorad probably can be achieved, the path length stability won't be achieved. Yes.
Okay. So given that we are late, I think I have to thank you again for reporting on this, on the progress that you are making on this alternative implementation for LISA. And I thank all the speakers. I'm sure that you will get some questions offline. I thank all the speakers. I think I close this session here. And Harry maybe wants to. So.
No, I think that's fine, Rita. Just to thank everybody for their contributions, and we look forward to seeing you all tomorrow at the beginning of the next session, which, remember, is a morning start tomorrow for those in Europe.
11 o'clock, right?
Correct.
Thank you.
So, good night all.
Yeah, good night.